In this video, we solve problem 10.2.081 from Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. The problem statement says, consider a projectile launched at a height h feet above the ground and at an angle theta with the horizontal. If the initial velocity is v0 feet per second, then the path of the projectile is modeled by the parametric equations below. The center field fence in a ballpark is 10 feet high. So this is meant to be the fence over here. And it's 400 feet from home plate. So here's home plate. If you look at this from just the right angle, you've got 400 feet here and then a 10-foot high fence there. Then the question says the ball is hit at h equals 3 feet above the ground. It leaves the bat at an angle of theta degrees with the horizontal, so that's parallel to the ground, at a speed of 103 miles per hour. First, we're asked to write a set of parametric equations for the path of the ball, and we want our equations in terms of both theta and t. So all we really have to do is substitute in the right value for v0, that's our initial speed in feet per second, and the value for h. Well, we were told that the ball is hit at h equals 3 feet above the ground. So this is initially 3. And then v0, that is this 103 miles per hour, but it has the wrong units. We need that in feet per second. So we're going to have to do a little bit of dimensional analysis to convert from miles per hour to feet per second. This actually isn't too bad at all. It's pretty straightforward. We're taking 103 miles per hour, and then we're going to multiply as necessary in order to get rid of these units and get to a number of feet per second. So if I'm trying to get out of miles and into feet, I'll put miles in the denominator and feet over here. That way the miles cancel. Well, it turns out that in 1 mile, there are 5,280 feet. If we multiply straight across now, we're going to get some number of feet per hour. That's not what we want feet per second. So we need to get from hours to seconds. One way that you can get from hours to seconds is to go through minutes. So I can convert from hours to minutes, and then I can convert from minutes to seconds. And that'll work because when hours are in the numerator and denominator, those cancel. And when minutes are in the numerator and denominator, those cancel. And the only units that we have left here are the feet in the numerator and the seconds in the denominator, which is exactly what we want. Okay, so that's the plan. We just need to fill in the right numbers here. 1 hour is 60 minutes and 1 minute is 60 seconds. So then if we multiply straight across, we're going to get some number of feet out of 103 times 5,280 feet out of 3,600 seconds. And so I get 2,266 over 15 feet per second. That's my v0. Okay, with that in mind, my x value is given by this formula. That's v0 times t times cosine of theta. And my y value is given by this formula. It was our h value, which was 3. That was in the problem statement, plus v0 in feet per second times t times sine of theta. And we're subtracting 16t squared. And I think they want this entered in my lab, or not my labs, in WebAssign, just as a comma separated list. So just type this in, comma, and then type this in. Now in part B, we're asked to use a graphing utility to graph the path of the ball when theta is equal to 15 degrees. And we're asked if it hits a home run or not. The question is, if we have an initial angle of theta equals 15 degrees, does the ball get to the 400 feet mark? Does it even get to the fence? And if it does get to the fence, does it go over the fence? So when x equals 400, I guess the question is, well, what's the y value there? There are a couple of ways that we could solve this. They are suggesting that we use a graphing utility. That's probably the easiest way. So let's try that. I will show you how to do this through an application online. Okay, guys, so this is pretty cool. If you just Google graph parametric equations, this is one of the top hits. You just go to desmos.com and it gives you an outline of how to graph parametric equations. So it says, if you want to graph a parametric, just make each coordinate a function of t and then click on the domain to change it. So we want our x value to be 200 or 2,266 over 15 times cosine of 15 degrees. And I wonder how it takes that cosine of 15 degrees. I wonder if you have to convert first. Well, just to be safe, let's multiply by the right conversion factor. So we know that there are pi radians in 180 degrees. So that would give us the cosine of 15 in that case. And then I want sine of 15. Multiplying by pi and then dividing by 180. I want to check in my scientific calculator to make sure it's calculating this correctly. Cosine of 15 is supposed to be 0.965 and sine of 15 is this 0.2588. So, okay, we have to convert to radians first. So this is my cosine factor for my x term. So all of that's being multiplied by t. And the y value is 3 plus that initial velocity, 2266 over 15, times sine of this guy, times t. And then we're going to subtract 16t squared. I don't want t to just go from 0 to 2. Let's let it go from 0 to 100. And I also want x to have a certain range, so let's mess with this a little bit. Let's let x go from 0 to 420. Okay, and that's what we want. Do you see what happened? As x goes from 0 to 400, that's where the fence is. It looks like the ball actually hits the ground somewhere between, if that is 350, that's 360, it's 370. So the ball actually hits the ground at some x value between 360 and 370. So it never actually makes it to the fence. So this is not a home run. So the answer to B is that no, this hit is not a home run. Now for part C, we're asked the same question, but we're asked to change our theta value to 23 degrees instead of 15. So I'll change that to 20, or that 15 into a 23. And then let's change the values here. I want my y values to go from, let's say, 2.5 to, let's say, 45. I don't know if you guys can see it. Let's zoom out a little bit. So the question is, does this ball clear the fence? I think it does. As t goes from 0 to 100, it looks like x does pass that fence. The ball actually gets to this point where x is equal to 400, and it gets to that point when y is approximately equal to 40. And the fence is only 10 feet tall, so that's plenty high over the fence. It's clearing the fence by quite a bit. So at 23 degrees, that ball is clearing the fence, so we can say yes, that is definitely a home run. But notice that at 15, oops, I messed it up, it didn't clear the fence. It didn't clear the fence at 15, but it cleared the fence at 23. So somewhere between theta equals 15 and theta equals 23 degrees, our function, or rather our ball, is able to clear the fence. The question is, what is the minimum angle at which the ball must leave the bat in order for the hit to be a home run? Well, I guess we could have stayed in Desmos and just played with it and just thought about how that parametric equation, like the graph of those parametric equations, would change as we took on different values of theta. That's one way of exploring. Another way is to solve the problem algebraically. We know that when x is equal to 400, we need y to be equal to some number that's greater than 10. So my question is, like, what is the exact value of theta so that when x is equal to 400, y would equal 10, so that we would just barely clear the fence? What theta value is that? Well, that's going to require a little bit of algebra. So remember, our x value is this 2266 over 15 times t times cosine of theta. And y is equal to this. Now this is somewhat complicated, because even if x is equal to 400 and we say let's force y to equal 10, we've still got these two equations and two unknowns, but the equations are unusual. I mean, this kind of looks like a polynomial in t, but it's got this trig function, and this has a trig function as well. So what I'd like to do is I'd like to write this entirely in terms of theta and then solve the corresponding equation for theta. So in order to do that, I think I will solve this equation here for t. So let's multiply both sides by 15, and then divide both sides by that 2266, and then also divide by cosine of theta, or multiply by secant, same thing. And then you find out that t is equal to that value. So if I substitute that in down here, and maybe subtract that 10 from both sides, we'll have 0 equals -7 plus 2266 over 15 times my t, which is 6,000, over 2266 times secant of theta times sine of theta minus 16 times t squared, which is that number squared. Let's simplify first. So we'll have 3,000 over 1,133 squared, and then we've got a secant squared in the denominator here. Wow, that's pretty ugly. And then we know that 15 goes into 6,400 times. So we end up with this. 0 equals -7 plus 400. And then we've got sine times secant, that's sine times 1 over cosine, is tangent of theta. And then over here, we've got minus 16 times this 3,000 squared over 1,133 squared, and then 1 over secant squared. I guess we could leave it like that if we wanted to. Or you could just write that as cosine squared, couldn't we? Now wait a minute, I don't know why it should be a 1 over secant squared. It should just be a secant squared. This because this is supposed to be a t squared, so that's just a secant squared. Okay, so we've got that. Now it's kind of ugly, it's kind of bad, but this is just an equation involving tangent of theta and secant squared theta. Now normally if I were in trig class, I would try to get this all in terms of one trig function. And we can do that because secant squared is actually tangent squared plus 1. So let's substitute that in here. So we're going to have 0 equals negative 16 times this 3,000 squared over this 1133 squared times tangent squared. And then we're subtracting that, because if I distribute that to the positive one there, I get this. And then I am going to add 400 times tangent of theta and subtract 7. And then we'll see what we get. Let's simplify those ugly coefficients. So I've got negative 16 times 3,000 squared divided by 1133 squared. So I have approximately negative 12 or negative 112.1767 times tangent squared here, minus, well, that's the same quantity, and then we're subtracting 7 from that. So that would make that there, make that value. Now, this is very ugly. This is not a pretty equation, but it's solvable. You know, the coefficients are not that nice, but this is just a quadratic equation in tangent. So this is u equals, if we let u equal tangent of theta, this is 0 is approximately equal to negative 112.1767 times u squared plus 400 times u minus 119.1767. That can be solved for u using the quadratic formula. So we'll say u equals negative b plus or minus the square root of b squared minus 4 times a times c. Oops, I did c times a, but that's fine. All divided by 2 times a. So I have 400 squared minus 4 times 119.1767 times 112.1767. Now, if you're saying, well, it's just negative times a negative times a negative is going to be a negative. So I've got that negative in front of that 4. And so that's what's under my radical. And I want to take the square root of that number. And so I've got that 326.3811. So I'll have u equals negative 400 plus or minus that value. And then we're dividing by this expression in the denominator. 112.1767 times 2, but it's going to be negative. So negative 224.3534 approximately. Okay, so we have two values of u. U equals negative 400 plus the 326.3811 over the negative 224.3534. And u equals the same thing, but with a minus sign in the numerator instead. Now both of these are equal to u, which is equal to tangent of theta. So then once I find the value of the tangent of theta, then I can take the inverse tangent to find out what theta is supposed to be. So let's figure out what that is. Okay, so I entered these into my calculator and I got these two values. In order to get theta back, I took the inverse tangent of both of them And then I got these two angles. The smallest angle that will give us what we want is apparently this 18.159. I would round to 18.2 degrees. Now there may be some rounding error here because we used a lot of rounded values. So maybe 18.2 isn't correct. It might be 18.1 or 18.3 or something like that, because of the rounded values that I used as I was solving this problem. So let's go back to that original problem statement. Find the minimum angle at which the ball must leave the bat in order for the hit to be a home run. Based on my calculations, that was 18.159 degrees. If we want to round to one decimal place, we could round that to 18.2 degrees.